astronomy, there are discoveries, and then there are revelations that force us to tear up the textbook and rethink the rules of the universe. For decades, we've had a comfortable model for how planets form. We have rocky planets like Earth and Mars, and we have gas giants like Jupiter. We thought we had the basics figured out, and then they found 55 Cancri E. It's an exoplanet, a super-Earth about 40 light-years away. And when scientists first pointed their instruments at it, the data they got back didn't make any sense. It was too dense to be a gas giant, but its composition didn't look like Earth's either. One of the first and most explosive theories to come out was that this planet was made of diamond. Now, further research has made that theory more complex. It's likely a lava world with a thick, choking atmosphere. But the question it raised has never gone away. The possibility of a diamond planet wasn't science fiction. It was a real scientific hypothesis. It forced us to ask a new, shocking question. What if our solar system isn't the default? What if there are other, stranger recipes for making a planet? This is the shocking science of extreme planetary composition. It's a revelation that what we see as treasure could, on a planetary scale, create the most terrifying and unstable worlds in the cosmos. To understand how, you have to forget everything you know about Earth. It all comes down to one simple cosmic ingredient list: the carbon to oxygen CO ratio. In our solar system, oxygen is more abundant than carbon. This is the most important fact about our home. With more oxygen, our chemistry is dominated by it. We have H2O, water. We have silicon dioxide, SiO2, which makes the silicate rocks of our crust. Our planet is made of water and rock. But what happens in a solar system where the recipe is flipped? What if you're in a part of the galaxy where carbon-oxygen? The chemistry changes completely and terrifyingly. There's not enough oxygen to make water. All the oxygen gets locked up by carbon, forming carbon monoxide, CO. The leftover carbon is a free-for-all. It bonds with silicon to form silicon carbide, a substance used to make bulletproof vests and industrial-grade saws. It bonds with hydrogen to make methane, CH4, and a host of other hydrocarbons, and the leftover carbon becomes graphite. Imagine this new solar system. It doesn't have rocky asteroids. It has carbide asteroids. It doesn't have comets made of ice. It has comets made of dry ice and frozen tar. When a planet forms here, it won't be a world of water and silicate rock. It will be a world of carbides, graphite, and tar. And if this planet is a super-Earth, big enough and hot enough, something magical and horrifying happens to all that graphite. Deep in its mantle, the staggering pressure and heat would begin to crystallize it. This planet wouldn't have a mantle of molten silicate rock like Earth's. It would have a mantle of diamond. This isn't just a revelation. It's a blueprint for a new kind of world. But what would it be like to stand on this planet? We think of diamond as a treasure, but when it's the crust under your feet, it doesn't just create a new kind of geology, it creates a planet-sized destabilization. This is where the revelation becomes a horror story. We think of a diamond mantle as a treasure, but from a geological standpoint, it's a death sentence. On Earth, our mantle is viscoelastic. It's a semi-molten flowing layer of silicate rock. This flow is what allows our continents, our crust, to move. This is plate tectonics. Plate tectonics is the single most important life-giving feature of our planet. It's Earth's thermostat. Here's how it works. Volcanoes at plate boundaries release CO2, warming the planet. Then, the weathering of silicate rock, also at plate boundaries, consumes CO2, cooling the planet. This is the carbon-silicate cycle. It's a perfect feedback loop that has kept Earth's climate stable enough for life for billions of years. Now, look at our diamond planet. Its mantle is not a flowing plastic. It's a solid, ultra-rigid trillion-carat crystal. It doesn't flow. It can't flow. This means no plate tectonics, ever. The planet's crust would be a stagnant lid, a single, seamless, and brutally hard shell of silicon carbide. And a planet with no plate tectonics is a planet with no thermostat. This is the first destabilization. Any heat from its star or its own core just builds and builds and builds. The climate has no way to regulate itself. It would be a world of unimaginable permanent temperature extremes. But the geology gets even stranger. What about volcanoes? On Earth, volcanoes are vents for molten silicate rock, magma. Our diamond planet has no silicate rock. It has no magma, so does it even have volcanoes? Yes, but they would be terrifying. The planet's core is still hot. That heat must escape. It would build up under that stagnant carbide lid, creating pressure that is beyond our comprehension. The crust wouldn't bend, it wouldn't shift, it would just fail. Instead of earthquakes, this planet would have diamond-quakes. The ultra-hard carbide crust would shatter catastrophically, releasing the energy of 1,000 nuclear bombs in a single planet-shaking fracture. And from these fractures, a new kind of volcano. It wouldn't erupt with lava. It would erupt with the only things that can melt, the lesser carbon compounds. Pockets of superheated, pressurized methane, ethane, and literal tar would be blasted to the surface. Imagine a geyser miles high of black, sticky 2,000-degree oil instantly igniting in the atmosphere. These aren't volcanoes. They are asphalt canoes. This, in turn, creates the atmosphere. It would be a nightmare. No oxygen, of course. That's all locked up. The air would be a thick, choking, and possibly flammable smog of carbon monoxide, methane, and tholins. The complex, gungy organic tar that results from this chemistry. The sky wouldn't be blue. It would be a permanent, toxic orange-brown, like the sky over Saturn's moon, Titan, but thousands of times thicker. And this brings us to the shocking irony. We call this a treasure world, but it's a resource-rich trap. On Earth, diamond is valuable because it's rare. The rock under our feet is life-giving silicate, which erodes into nutrient-rich soil. Our resource is a crust that gives us food, water, and a stable climate. On a diamond planet, the rock is silicon carbide. It's an industrial abrasive. It would never erode into soil. It would just break into smaller, sharper, sterile pieces of sandpaper. The treasure is graphite, the stuff in your pencil. The valuable liquid is methane, natural gas. You could not grow a single plant. You could not drink a single drop of water because there is none. The most valuable, precious, and scientifically world-shattering treasure you could ever find on this diamond planet? The one thing that would be rarer than a mountain of diamond, H2O, a single cup of water. The ultimate destabilization this treasure creates is biological. A planet like this is not just hostile to life. It is fundamentally chemically sterile. Life, as we understand it, needs one thing, a solvent, a liquid that can move chemicals around so they can react. For us, that solvent is water. It's the universal solvent, a superpower molecule that can dissolve almost anything, allowing for the complex chemistry of a cell. Our diamond planet has no water. The only liquids on its surface would be pools of non-polar hydrocarbons, tar and methane. Trying to start life in a puddle of tar is like trying to build a computer in a vat of Vaseline. The chemistry just can't. The molecules are too simple, too sticky, and they don't dissolve the things needed for life. So this is the grand, shocking revelation. A planet can be too rich. We look at a diamond, a perfectly ordered crystal of pure carbon, and we assign it value based on its rarity on Earth. We've built entire economies, fought wars, and based mythologies on this one shiny material. But the universe doesn't care about our economy. The universe operates on chemistry, and the chemistry of a diamond planet is the chemistry of sterility. It's a world where the crust is an abrasive, the mantle is a rigid prison, the air is a toxic fog, and the rain is a flammable, sticky ooze. It's a planet that is geologically, climatically, and biologically dead on arrival, a stagnant, choked, and unchanging world. The discovery of 55 Cancri AE and the diamond planet theory it inspired is one of the most profound in modern astronomy. It's a revelation that has forced us to reevaluate our own home. It teaches us that our planet is not boring. Our boring silicate rocks are the engine of our climate, the source of our soil, the foundation of our world. Our boring water is the single rarest and most powerful ingredient for life, a cosmic solvent that makes everything we know possible. We've been searching the stars for a second Earth, but the shocking truth that these extreme planets reveal is how unbelievably lucky our first Earth is. It turns out that the greatest treasure in the cosmos isn't a planet made of diamond. The greatest treasure is a boring planet of water and rock, a planet that is unstable enough to have plate tectonics, an atmosphere, and a climate. A planet that, instead of hoarding its resources in a perfect dead crystal, uses them to create the one thing that is truly priceless: change. And from that change, over billions of years, comes the greatest prize of all: life.